Hello everyone. Today we'll be discussing about the power factor improvement. In the previous lecture, we already discussed what is a power factor, what are the ill effects of low power factor, and why should we improve the power factor. So, now today we will discuss about the methods, the way in which we can improve the power factor of the system. Basically there are three methods to improve the power factor. The very first one is a static capacitor, second one is a synchronous condenser, and third one is a phase advancer. Right? So, very first one we will discuss about the static capacitor. Now, the static capacitors are connected in parallel with the equipment operating at low power factor for the purpose of the power factor improvement. So, the static capacitors are connected across the motors, across the arc discharge lamp, across the induction welding, induction heating. So these are the equipment which draws heavy amount of inductive reactive power. And for this, the capacitor is connected across the devices. Now, this capacitor when connected in parallel produces or generates the leading current. And this leading current will partially or totally neutralize the lagging inductive current. Right? So the power factor of the circuit gets improved. Now these capacitors are installed across generally large inductive loads, induction motors, transformers, and they improve the load circuit power factor to improve the system efficiency. Right? So here is a diagram which shows the connection of capacitor across the load. Now consider the diagram first, in which a voltage V is supplied and current I1 is flowing to a load which consists of a resistance R and an inductor L. Right? So basically load is RL in nature. Right? Due to this load, our current I1 is lagging the voltage with phi1 angle. Right? So in diagram third, when a capacitor C is connected across the load RL, the capacitor draws a current IC. The load draws current I1 that was as same as the previous, and the voltage source is supplying current I2. Right? So in phasor diagram fourth, we will find that the current I1 is lagging by a voltage by an angle phi1 with the voltage. Current IC, which is leading the applied voltage by an angle 90 degree as it is capacitive current, and the phasor sum of I1 and I2, which makes the current I2 is equal to nothing but I2, which is lagging the applied voltage by an angle phi2. Right? Now from diagram fourth we can observe that the phi1 is very much high than as compared with the angle phi2. So the power factor is getting improved. So after the power factor improvement, the circuit current would be less from the low power factor circuit. Right? So the active power would be same after and before the power factor improvement, but the reactive power changes. Now we will be calculating the value of the capacitor that is being used for the static capacitor. Right? So the VAR1 and the VAR2 are the reactive power corresponding to the power factor 1 and the power factor 2. So the power factor 1 produces the VAR1 and the power factor 2 produces the VAR2. Right? So VAR1 is nothing but equal to W10 of phi1, which is equal to W10 cos inverse power factor 1, and the VAR2 is equal to W10 phi2, which is equal to W10 cos inverse power factor 2. Now, what the VAR is capacitor is compensating is equal to the difference between the two VARs before the power factor improvement and after the power factor improvement. So before the power factor improvement, the VAR is VAR1, and after the power factor improvement, the VAR is VAR2. So difference between the two, VAR1 and VAR2, is equal to VAR. This VAR is being compensated with the help of capacitor. So the reactive power QC is improved the power factor from cos phi 1 to the cos phi 2. Therefore the QC is equal to VAR1 minus of VAR2. Now we know that the QC is equal to V of IC and IC equal to V divided by XC, which is equal to V of omega C. Therefore the QC can be written as V square by XC, or QC is equal to V square omega C. The value of C can be calculated in terms of farad, and it is given by QC divided by omega V square, or QC equal to 2 pi f V square. The value of omega is equal to 2 pi f. Now this is being calculated for the single phase circuit. For three phase delta connection, we know that the line voltage is equal to the phase voltage, and the rating of each capacitor for the delta connection is given by QC divided by omega VL square. Now for three phase star connection, the phase voltage is equal to line voltage divided by root of 3. Therefore the rating of each capacitor for a star connection is equal to 3 QC divided by omega VL square. Now there are the certain advantages and disadvantages of using capacitor bank. So the very first one, we will discuss the advantages of using static capacitor bank for improving power factor. So the losses are low in the static capacitor. There are the less losses in a static capacitor. There is no moving part, therefore need low maintenance. Right? It can work in normal air conditions, right, ordinary atmospheric conditions, and do not require any foundation for installation. The installation foundation is required in case of synchronous condenser. They are lightweight, so it can be easy to install and uninstall. Right? So, but there are certain disadvantages also of using static capacitor. The age of static capacitor bank is less, about 8 to 10 years. So after 8 to 10 years, you have to replace the static capacitor bank. With changing load, we have to on or off the capacitor bank. So it will cause us switching surges. Right? So whenever we switch on or switch off the capacitor bank, it will produces surges. If the rated voltage increases, then it causes damage to it. The capacitors are designed for a rated voltage. If a voltage greater than rated voltage is applied across the capacitor, then it surely will get damage. Now once the capacitor is spoiled, then repairing is costly. So whenever capacitor bank get damaged, it's cost high to repair them. The second method to improve the power factor is synchronous condenser. Right? So when a synchronous machine is operated at no load, it is called a synchronous condenser. Right? So a synchronous machine working on no load is a synchronous condenser. When it's overexcited, it can work as a synchronous capacitor, and whenever it's underexcited, it will work as synchronous condenser. But there is a difference between the two working. When it is overexcited, it provides leading current and work like a capacitor, and when it is underexcited, it will consume the lagging current, and it works like a inductor. So when a synchronous condenser is connected across supply voltage, it draws leading current and partially eliminates the reactive component, and by this way we can improve the power factor of the system. A synchronous condenser is used to improve power factor in large industries. Right? So here we will find how the synchronous condenser is connected. Consider a three-phase load which is being supplied with the current IL, that is load current. The total current which is flowing in the system is equal to I, and the current that is being drawn by the synchronous condenser is equal to I of M. Now in the phasor diagram we will find that the current IL which is being drawn by the three-phase load is equal to IL, and it is lagging by angle phi 2. The total system current is being lagging by an angle phi 1, and the current that is being drawn by the synchronous condenser is leading the voltage by an angle phi of M. Right? So in case when there is no synchronous condenser, then this I will be equal to I of L. In that case, the power factor of the three-phase load will be equal to 5:1. So by connecting a synchronous condenser, the current that is drawn by the synchronous condenser is Im, and the power factor is getting improved to an angle phi of 2. Right. So what are the advantages of using synchronous condenser? It has a long life, almost 25 years. High reliability, established adjustment of power factor, as compared with the static capacitor, in which we have to on or off the capacitor based on requirement. In case of synchronous condenser, by controlling the excitation, we can easily adjust the power factor of the system. There is no generation of harmonics. The fault can be removed easily. It's not affected by the harmonics, and it is require low maintenance. Only periodic bearing greasing is necessary, right? But there are the certain disadvantages also. It is expensive. The maintenance cost is also high, and therefore mostly used by large power user. An auxiliary device has to be used for this operation because synchronous motor has no self-starting torque and it produces noise. So the third method for improving the power factor is phase advancer. So the phase advancer is nothing but a simple AC exciter which is connected on the main shaft of motor, whose power factor is to be improved, and it operates with the motor rotor circuit for power factor improvement. Right? So phase advancer are the AC exciter which are connected on the main shaft of the motor, whose power factor is to be improved, and the operational power it's been getting from the motor rotors circuit. Phase advancer are used to improve the power factor of induction motors in industries. Right. So the AC stator winding of the induction motor takes lagging current at 90° out of phase with voltage. Therefore, the power factor of the induction motor is low. It will take a 90° lagging current. Right. Now, if the exciting ampere turns are excited by external AC source, then there would be no effect of exciting current on stator winding. Right. This is the basic concept behind the AC exciter. So the AC exciter provides exciting ampere turns to the induction motor, whose power factor is to be improved, and therefore the power factor of the induction motor will be improved. This process is done by phase advancer. Right. Now there are certain advantages of using phase advancer, that lagging KVR, reactive component of power or reactive power drawn by the motor, is sufficiently reduced because the exciting ampere turns are supplied at slip frequency. The phase advancer can be easily used where the use of synchronous motor is unacceptable, right? But there are the certain disadvantage. That is a major disadvantage of phase advancer is that they are not economical for motors below 200 HP. So for the motors above 200 HP, only the phase advancer can be used. Thanks for watching.